Okay. So let me, as usual, start summarize. Well, as usual, as yesterday, the day before, summarizing where we were before I continue. So on Wednesday we saw a little bit of the the main features of the geometry of the nilpotent cone. So remember that. So on Wednesday. We saw that given a Higgs bundle inside the nilpotent cone, which remember that it's Lagrangian and pure dimensional scheme, which is in fact non-reduced and reducible. Then there is a filtration associated. So it's the iterated kernel filtration. Sorry, this is not. Can you see my whiteboard? I somehow switched applications. Is it? Can you see it still?
Yeah, I can still see it.
Okay. Okay, great. Right. Then we have the iterated filtration, kernel filtration. So the kernel of phi contained on different, well, or equal could be, but only when we reach the highest potency order, kernel phi squared, and so on until okay. Now, so the EIs are the successive kernels, and this produces a graded object whose pieces are given by quotients like this. And to these filtrations, we associate some invariants. So the tuple n with ni, the rank of f, I, and d, the rank of, the degree of fi. And these, in fact, classifies the reducible components of the nilpotent cone. So there will be Higgs bundles in the moduli space, such that the filtration, so the filtration, the degree of Fi equals Di, and the rank of Fi equals Ni. Okay. Also, we're talking about a particular locus in the moduli space in the nilpotent cone, which is on the wobbly locus, which consists of Higgs bundles, which are stable or semi-stable and admit a non-trivial nilpotent Higgs field. We also saw a counterexample. So some semi-stable wobbly will not have their nilpotent Higgs fields seen, say, by the moduli space. So what we can state is that the stable wobbly locus is equal to the intersection of all the components with non-trivial filtration, right? If I just take the trivial filtration, then I have only one step here, so it would be just the zero nilpotent Higgs field can work. So then we would have intersection of irreducible components. Okay, so strictly speaking, this is not an irreducible component. Okay, I will have used notation. This is a stratification. So the closure of these sets give the irreducible components. Let me abuse notation to avoid extra bars. So these will be the irreducible components from now on. Okay, and I should say stable. Okay, so we stated Donagi-Pantev's conjecture, which they proved, although the proof is not published, I think. I mean, they state this in their notes, but I haven't seen their proof. They conjecture that the wobbly locus equals the shaky locus. And this shaky locus was obtained via some resolutions. So we have a rational map. There's a rational map from the moduli space of Higgs bundles to the moduli space of bundles. So suppose that the moduli space is smooth, which is the case I'm going to treat now. By blowing up along the unstable locus in here, one obtains a resolution whose exceptional divisor maps. So this is the resolution, this is R, and this is high. So R of X is by definition the shaky helix. Okay. Okay, so the goal is, amongst other things, is to prove this. Hopefully we'll get to Drinfeld's conjecture as well. So let's retake now. I promised to tell you, so a priori, we have, so the definition of the wobbly locus, of course, it has to do with the nilpotent cone, but it's not clear how crucial this nilpotent cone is in the definition. Okay, we have this property, that's true, but in fact, let me show you now that that it has everything to do with the nilpotent cone, and in particular the Hitchin map. So the first theorem, let's see, theorem. So this was joined with Pauli in 2018, I think, and Selassie proved a beautiful generalization that's extremely useful. So it's also very basic, but it's more of an algebraic proof. So I encourage everyone to read this paper, which is really nice. But I'm going to give the geometric proof now. So suppose that we have a stable vector bundle. Then E is very stable. If and only if HE, which by definition is the restriction of the Hitchin map to the space of Higgs fields on E. Let me set up some notation. This is from now on going to be called VE, okay, for vector space associated to E. So this goes to the Hitchin base. So it's proper. Okay, so the proof is very elementary and really nice. So this direction is was known. I mean, this is nothing new. It's very easy. So as John remarked in the chat on Slack, what happens here is that a proper map between affine spaces is finite. So affine spaces, sorry, of the same dimension, okay? The dimension of VE is 1/2 the dimension of the moduli space, which is 1/2 the dimension of the Hitchin base. So proper implies finite, and therefore if it is wobbly, since it is stable, we can say that there is a line inside the moduli space for any given nilpotent Higgs field on it. So there's no implication here, sorry. So if is wobbly, nilpotent. Okay, so the stability assumption comes in here, right? Because there are no automorphisms taking any element of this line to one another, and therefore they give different points in the moduli space. This is not true, as we saw in the counterexample for stable guys, for strictly semi-stable guys. Right, so there's a line over the Hitchin base, right? So HE minus 0 is not finite. So this contradicts properness. Sorry, let me maybe you had to have a look. Okay, so what's interesting is this direction, that variability implies properness, and it's moreover in here where we see how crucially the nilpotent cone intervenes. In fact, it's already here. This is what makes things fail, but that's essentially by definition. Right. So suppose now that VE is not proper. So this is equivalent to seeing that this is the evaluative criterion for properness. It's equivalent to seeing that there's a point in the closure that does not belong to the vector space. And it's easy to see by separability of the moduli space of bundles then that it forces by the point to have an unstable. So for any such Fi, F is unstable. Otherwise, we would have two limits of the constant sequence on the moduli space, one to F and one to of the constant family. Right, if F were semi-stable, right? One to F and one to E. Okay, but then let me just draw a picture. So we have here our VE with its point at the closure. So this is FC. And this is VE. So now the C star action, let's flow things to the nilpotent cone. So we multiply C by T, and it's from Schatz's work, it follows that the limit has to be unstable as T goes to 0. Okay, you can't have an unstable bundle degenerate to a stable guy. So this is this is on fixed point component of the nilpotent cone. But all the rest, I mean, VE gets contracted to a point, right? VE without the closure gets contracted to a point by the C-star flow. It all flows down here. Right. Okay. So the thing is, in this way, we're defining a surface. So we have C times yeah. Right. So we're defining a map, but it's a rational map because it's not defined at 0. Okay. Because the limit, it's once we fix the point in here and the limit is defined. Because so Dong asks why we can assume that F is unstable. It is because of separability of the moduli space. If F were unstable, then we could always approach F inside the moduli space through a curve, a constant curve with underlying bundle E. But this is not possible because the moduli space is separable. So we cannot have two limits of the constant sequence. Okay. Right. So in this way, we find a rational map from C times this closure of the vector bundle into the modular space of Higgs bundles, but it's not defined over 0, precisely because of this non-matching of the limits. So one can blow this up finite number of times, and this will produce a divisor.
Anna, your audio is
which will hit. Say that again.
Your audio is occasionally breaking up. Just a heads up.
Yeah, this is the connection. I'm so sorry. Is there something important that's missing? Just prevent me when I have to repeat, because I can't do much more.
No worries. I'll give you a warning. I'll give you a warning if there's something you need to.
Please do. I'll repeat. Okay. So now the idea is that blowing this up, this produces a series of divisors in this surface. So in fact, the easy way to go, so it's to fix a curve. So we can always approach. So we want a surface here. This is a curve approaching FC from VE, from within V, right? We can assume the curve is contained inside the vector space except for the limit point. So this would give there you go, a surface with a rational map to the moduli space. And as we flow it, everything will be contracted to E0. Okay, we have assumed that E is stable, except for this point. So now, after a number of blow-ups, one can produce a divisor which will connect the limit. So there's a union of P1s that connects. This is the exceptional divisor, F0, C0 to E0. All right. But then one of the components is forced to intersect E0 and a component of the nilpotent cone that's not the moduli space. And this implies that E0 is wobbly. E is wobbly. When it's to C, so this implies that E is flown in from outside of the nilpotent cone. So E is okay. All right. So if we look at the proof now, we see that VE is not the same as its closure, if and only if VE intersected with the nilpotent cone is not the same as its closure, right? It's not a very hard proof, it's just the C-star flow, but it's sort of a nice remark. Right, so the first corollary we get from this theorem is the following. So as I said, it's due to Bovil, Narasimhan, and Ramanan for generic fibers. But it holds for any fiber. And why is that? Well, it's just properness implies finiteness, and by dimensional reasons, it has to be surjective. So we have if we take a very stable bundle, then we have that the space of Higgs fields on the vector bundle has to intersect every fiver for all B's. And why is that? Well, because HE is finite. And it therefore has to be surjective because we're working with affine spaces of the same dimension. Okay, so the picture for a very stable bundle would be the following. If it's very stable, then over a generic point, we will have a finite number of points. And these will float to the same point on the nilpotent cone. And a nice remark of this is that by finiteness of the, by flatness of the Hitchin map, this point will have the multiplicity given by the cardinal of the pre-images over generic fiber. So this was computed by Balasubramanian, I believe. Hitchin and Housel also developed this a bit further in their recent paper. Okay. So let me prove the Nilpotent conjecture for smooth moduli spaces. Okay, so we are assuming now that the rank and a degree are co-prime. So with the notation we established, namely, we have a resolution of the rational map given by a finite number of blow-ups over the unstable locus. So the theorem is that the image of the exceptional divisor is the wobbly locus. Are there any questions so far before I proceed to?
I don't see any in the chat box.
Okay, so let me continue. So this is again another.
I'll ask a quick one, Anna, if that's okay.
Okay.
So,
yep.
So is this also known for the case with punctures, parabolic?
Yeah. So I mean, this is using. I mean, at least in the moduli space. In the case of P1 minus 5 points parabolic structures, then yeah, it.
I think that's there in their paper, right?
That's in their paper, but the way they use, I mean, it's a totally different proof. I mean, they just verify which the wobbly locus is, and they compute the shaky locus. So there's no, I mean, not that I've detected. I'm not sure their strategy generalizes. I don't think it does.
Okay. Thanks.
No problem. Okay. So, yeah. So the proof is very simple. So let's see. Why should wobbly be shaky? So this is the shaky locus. The names are really good. I mean, Super. Let me draw it. Okay, so suppose we have a wobbly guy, then we have this picture again, right? So we have VE here, we have our FC, which has underlying unstable bundle, and then we have this curve that approaches it and gets contracted to E0, but through the, so this is the curve. Let me use another color, blue we had. So we contract the curve to E0, except for that point that goes to some higher fixed point. Right. So we need to somehow produce a shaky guy from this. Well, it's not very hard to guess how to do it, right? Because so there is a rational map. Let's take R, which is not defined everywhere, but it defines a curve in the moduli space, which is constant everywhere, right? So this is the map to N. It's constant everywhere, and by properness of the moduli space of bundles, it must have a limit. And this limit has to be E, right? Because it's constant and the moduli space is separable again. Okay. Right, and now the same, this is M. So let's lift things to the resolution. Now we have, and the moduli space is the same. It's one of the open rational that gives the birational morphism. And we can lift the curve, which by properness of the projection will have a limit as well. So this is a lift C hat, and the limit of C hat has to be shaky, right? Because it's above the pre-image of FC. So S is, it's not shaky, sorry. This shaky is not defined up here, but it belongs to the exceptional divisor. Well, there you go. You have your shaky guy just by mapping S to the moduli space, and this has to be E because, again, the curve C hat is mapped to C minus E, and this curve has a unique limit, which is E, and it's C. It's also R of S. Okay, so this proves that wobbly is shaky. Questions? Okay.
No, I don't see any.
Okay. Great. So now let's see the converse. So why are shaky bundle wobbly? Okay, so we start with something. We have a point here in the resolution. And so inside the moduli space, this has image, say S. FC somehow. So now, since M hat is quasi-projective, we can approach S from the moduli space, okay, which produces a curve down here and a curve under R hat in the moduli space. Let's switch to blue, it's nicer. So this is CC hat, and then we have in the moduli space, also a curve. Okay, now the extra difficulty is that this curve is not constant. It doesn't need to have the same underlying bundle in any of in any of these instances. So it will be a priori non-constant curve. The limit is shaky precisely because of S. So we have to see that it is wobbly. Okay, so in other words, we need to work here to connect F to some wobbly guy. So as before, we proceed by flowing this curve to the Nilpotent cone. Let's see screen. So the well, it's not contracted in this case. It is. It just gives the same curve as here. Okay. So we're here in the moduli space, but inside the Nilpotent cone. F will be flown to something different. But we have seen, right? This is the same argument as before. There's nothing new. After blow up, possibly, we will see that this limit has to be wobbly. But this limit and this limit are the same. Okay, so our shaky point is wobbly. So this is the proof of Donaghy and Pantev's conjecture in the smooth case. For non-smooth, moduli space is a bit trickier because you cannot resolve in this way. So you have to resolve fiber-wise, and then check that things also match. I haven't completed the details, but I believe it will be done through the C-star flow on maximal, towards maximal components of the Nilpotent cone. So this is work in progress. And yeah, I won't say anything further. So are there any questions about this part of the course? Oh, nope. Okay. Sorry?
I don't see any hands raised or questions in the chat box.
Okay. So let's move on to Drinfeld's conjecture. Let me read it like this because I firmly believe he did prove it, but just the proof is not available. So the statement is the following: the wobbly locus is of pure codimension 1. Okay, so I will prove this in rank 2. I hoped I could get to rank 3, but I won't have the time. Let's be realistic. But many of the ideas appear, well, at least for some loci, for at least for length 2 components, the ideas are present in the rank 2 case. So let me do some. This is 3 point.
Anna, you said something component that got eaten up. Can you just say that sentence again?
Which sentence, sorry?
There was something component. I didn't catch that.
Yeah. Okay, yeah. So what I was saying is that the ideas involved improving pure codimensionality of components of type 2. Yeah, sorry, N1 and 2. So length 2 filtrations are already present. Thing about the 2-1 type So there are some new components, but not very crucial. That what's new, it's different length components. So for that, there is an induction procedure that we are developing currently with Christian, but yeah, I won't have time to talk about that, unfortunately. Okay. Yeah. Okay. Is that now okay, Aswin? I lost you. Since
yeah,
I said,
yeah, that was okay. That was okay.
Okay. Okay. Some preliminary remarks. So what we're going to be doing is analyzing of the downward flow from the nilpotent cone. So we will have here, say, this is our moduli space. We want to understand the wobbly components, right? So a priori, I will consider loci that appear by contraction of components of the nilpotent cone under the C-star flow. So this is a component of a non-trivial type, and any Higgs field on a given stable guy will flow down to E0 from the nilpotent cone once we endow it with the nilpotent Higgs field. Okay, so now we have that for stable bundles. The space of Higgs bundles is a subspace of the moduli space. And it's also a subspace of the tangent space at E phi of the moduli space. For these, one needs to use that the downward flow one, that E phi is a smooth point, and the downward flow is a locally trivial Zariski vibration. So then if one has a Higgs field, whatever Higgs field, one can define by duality a hyperplane inside H1 of the endomorphism of E. And this is the tangent space at E of the moduli space. Okay. So if one manages to prove that a given vector bundle has a line of Higgs fields, only a line of Higgs fields that are nilpotent, then we have what we wanted, okay? Because it will belong to a unique component of the intersection of these irreducible components with the moduli space, and the normal bundle has no choice but being this downward flow. So we have proven the conjecture. Okay. So this is the main idea underlying the whole analysis. Right. So let me briefly mention some tool that's not so important for rank 2, but it will be in higher rank, which is the notion of a Hex Bundle Extension. So one may consider, given E1 phi1, E2 phi2, extensions of a form. So extensions of phi2 phi2 by E1 phi1. So these are exact sequences of Higgs bundles. Okay, so in the category of Higgs bundles. And these are parametrized. And this is Thaddeus' proof. His aim was to study the formations of parabolic bundles, but this extends beyond. So these are parametrized by a hyperchromology group. It's the first hyperchromology of a given complex. So we have the complex given by two complex. So one assigns to a given point, the composition with phi2 and subtracts phi1 composed with S. Okay. So if you're not familiar with hyperchromology, this is totally defined by a a long exact sequence. So we have H0 of the complex is well, yeah, it's a high instant function record. And so on H1 of C2 of C0, H1, E2, E1, H1 of E2, E1, okay, and then H2. And that's it. Okay, so as a remark, if one looks at H1, there will be two things that constitute a Higgs bundle extension. First, a bundle extension, and secondly, a Higgs field from E2 to E1. Okay, so indeed, the extended Higgs field respects E1 phi1 as a subbundle. But you know, not all extensions and not all Higgs fields will be compatible. There is some co-cycle condition, and if one analyzes what it has to do, for example, in terms of what it means in terms of check homology, for example, one sees precisely that the local form of the extension given by the cocycles have to define an extension such that the given field is a Higgs field on that extension. Right. So notice also that in particular, if we have a nilpotent Higgs field, then an nilpotent Higgs bundle is or can be realized as an extension, maybe in different ways. For example, of the kernel of the Higgs field with the zero Higgs field, and then E0 with some induced Higgs field. So it's not hard to see. Since we were only working rank 2, this will be always 0. Okay. So, but it's not hard to see that there's it generalizes. I mean, or if you think in local terms, you see from the matrix, from the standard form that this has to hold. Okay. Oh my God, I only have 15 minutes left. Or did we start a bit late, maybe?
Yeah, you can go a little over. It's totally fine.
Okay. Define little.
10
5
minutes?
minutes?
10 minutes?
10, oh, okay, 10 minutes, good. Then, okay, then I'll have time. Okay, so let's move on to the rank 2 case. So this is due to Paul and Pauline. So in rank 2, what do we want to do? Well, we want to parameterize extensions of the form F00. So in rank 2, the first graded piece, I mean, the first graded piece is always the kernel. So F0 equals E0. So we have to parameterize extensions of a given line bundle by another one, but with a Higgs field. So of course on the line bundles, the only nilpotent Higgs field is 0. So another remark here is that any nilpotent Higgs field will be totally defined if we consider the following sequence, and this goes back to the cohomology. So we have the kernel co-kernel. And then if we have a nilpotent Higgs field, then it will be totally determined if we know a section from F1 to, sorry, an amorphism from F1 to F0K. So phi will be of the form project, apply phi, C, sorry, C, and then embed, okay? So it's equivalent to know phi or to know this section. That's phi. All right. Perfect. So what we want. F0, F1. Well, that meet a section. Sorry, a morphism like this, right? So we have a priori, we have points in the Jacobian, say for given invariants. But we can map it to the Jacobian of degree delta. So what we want is for there to be sections of this bundle, right? Morphism from F1 to F0K. Say delta is the degree of this bundle, which is D0 minus D1 plus 2G minus 2. So we can map F0, F1 to the appropriate bundle, appropriate line bundle here, and then leave the other one, say D1 invariant. So we don't want to consider all line bundles, but we want to consider the symmetric space. The symmetric product of delta copies of X times, say, the Jacobian D1. So this is a subspace. In fact, we will take the Jacobian if delta is large enough. So if delta is greater or equal than G, then every bundle has a section. This is Riemann row. But if delta is smaller than or equal than G minus 1, then generically, line bundles won't have a section. So pulling back, we obtain our base scheme over which things will be constructed. Okay. Okay. So we have seen that from E phi we produce F0, so a point. We produce a point in Z, right?
Anna, what is Z?
Z, oh, sorry, Z is defined by the Cartesianity of this bundle. So it's pairs of line bundles F0, F0, F1, such that F1, F0 belongs to either the symmetric space or just the Jacobian, depending on how big delta is. And the other one, I mean, and F1 is just a line bundle. You take all line bundles. Okay. Okay. So it's just the pullback of this or the fiber product of this scheme over this one. Okay, so any nilpotent Higgs field produces a point in Z just by taking kernel, co-kernel, and psi, right? Kernel and co-kernel, sorry. Then we'll have to parameterize the psi. So to produce, our aim is the opposite, to produce E phi from Z. First, we need to add, we need an extension type. So an extension class, sorry. And the psi, okay? But first, let me comment on some necessary conditions for stability, right? So what does the invariant delta satisfy? Well, since we're starting with a semi-stable bundle in the nilpotent cone and D0 is the degree of the kernel, then we have that delta 0 has to be smaller than delta 1. So therefore, delta we're also assuming we're in a non-trivial component. So we can assume that delta strictly is
I know we lost
also a necessary condition for
a little bit.
Sections to exist here. Okay. So what I was saying is that this is the condition. It's a necessary condition for any bundle of that's given by any nilpotent Higgs bundle, which is given us by an extension of F1 by F0 to be semi-stable, because F0 is going to be the kernel, which is invariant by the Higgs field. So D0 has to be smaller than D1, and therefore the delta has to be smaller than 2G minus 2. Okay, this is for semi-stability. But we have another condition, which is the existence of an nilpotent Higgs field, which is equivalent to the existence of a section of this bundle. And therefore, we also need for delta to be at least 0. And if it is 0, then F0 has to be, F1 has to be equal to F0, okay. So this is for nilpotency. Existence of a nilpotent Higgs field, and this is for semi-stability. Okay. Okay, so let me rewind. We start with a nilpotent Higgs bundle. We managed to find a point in Z and an invariant that has to satisfy this. So now we're going to do the opposite. Starting from Z for these invariants, we can always construct. This is just a fiber product here. We're going to reconstruct the components of the nilpotent code. Okay.
So Anna, quick question. The inequality delta less than 2G minus 2, that's for semi-stability of the pair E5, correct?
That's for that's for, in fact, semi-stability and non-triviality of the Higgs field. If it's equal to 2G minus 2, then you would have to have a split polystable class. So it has to be in the moduli space.
Okay. Yeah.
Split semi-stable, sorry, class. Split polystable representative. Right. So the goal from Z delta 1, say delta built C delta 1. So I've changed the notation, right? But I know the degree. Knowing the degree and delta is knowing D0 and D1, which are the original. These are the original invariants that I attached to the nilpotent consolidate. So it's well, you can work it out, right? I think that's clear. Let me know already. We'll possibly do it wrong. So yeah, it's a linear system that's totally determined. So right. Well, the way to proceed is just through extensions, Higgs bundle extension. Okay. Right. So let me say the lemma. Is there a question?
I think we can wait till the end to just deal with all questions.
Okay, and this is a physics question. I think Aswin would answer it better. Okay, let me say the lemma. There exists a rational vector bundle with fiber given by the first hyperchromology of the appropriate complex. Okay. So what Paul and Pauli proved is the following. They proved that there exists a commutative rational diagram so from the projectivization of these vector bundles, so let me add the invariant into the moduli space. Also goes to the projectivization of the bundle over Z, which parameterizes extensions of F1 by F0. So let's call this R and R. That's not a very good notation. G. Oh no, this is R indeed, but the other one is not R tilde. Yeah, I called it hat. Sorry. So yeah, this is R tilde, which is not the same as the R hat. So such that one, the image of F of this projective bundle closed is the component with invariant delta. For all deltas smaller than or equal to 0, smaller than G minus 2. 2, the image of under F of this extension bundle is, say, call it, don't call it, is the wobbly locus of type delta, where it's not necessarily a divisor, okay? W delta for now, it is the intersection of the component with the moduli space. So these are the points to which this component flows down inside of the moduli space. And 3, this has codimension 1 for 0. So for delta in between 0 and G minus 1, I forgot to state, no, and G. I forgot to state that delta has to be congruent to the degree mod 2, right? But this is just because it's D0 minus D1 plus 2G minus 2. And the degree is D0 plus D1. So not all deltas will be valid. And W delta is contained in, so for delta greater than G, it's going to be contained in some locus of wobblies, which is the divisor for which delta is the maximum delta smaller than G. Okay. Okay. So here what's happening is precisely that for these invariants here, there's just one Higgs field generically. And this is not true anymore for the invariants that are, I didn't put it, but for the invariants that are greater than G. Okay, so let me do a dimensional count as a proof. Okay. First, the remark, I mean, the existence of a map is just by definition of the moduli space. It is rational because not all extensions will be stable. But by definition, the moduli space co-represents the modular functor, and therefore, whenever one has a family parametrizing semi-stable objects over the curve, there is automatically a map, because there is a transformation, a natural transformation between the functor and the home to mx functor. Okay, so this is the definition of a coarse moduli space. Same here. So assuming that there is such a morphism, then if we prove that the dimensions match, then it follows automatically. I mean, one needs to prove injectivity, but proving injectivity, generic injectivity, and having a dimensional count, then one has the statement, because all extensions are nilpotent. Is that clear, or should I explain further? It's been a bit quick, maybe. In any case, yeah, I can explain a bit more during the questions. Okay, so let's see. We have three elements, okay? We have the base scheme parameterizing the bundles we are going to be considered. Then we have the extensions. In this case, I didn't remark it, but the extensions is very simple because it's just the direct sum. In this case, it splits. But I wanted to explain this machinery because this is how one can easily generalize. Right, so we have two cases, delta greater than or equal to G and delta smaller than G. So when delta is greater than or equal to G, then we have that all Higgs bundles have a section. Sorry, all such line bundles have a section. So the dimension of Z is 2G, right? It's all the F1s, all the F2s. Also, we have that generically, it's not hard to see that this H1 is the Euler characteristic of F1, F0. Okay, minus the Euler characteristic of F1, F0 plus H1 of F1, F0. Okay, this would be H2 of the complex, and H0 is 0 because of the stability condition. Okay, well, plus H0, but this is 0. Okay, so let's see. This is just 2G minus 2. So H1 is 2G minus 2 plus whatever this is worth. So when delta is greater than G, it is, so this is the same as the sections from F0 to F1, which is a line bundle of degree strictly smaller than G. And therefore, generically, since we can consider all line bundles, this is going to be 0. This is only generic. Now, when delta is smaller than G, we didn't have all line bundles, unlike in the delta greater than G case. We only have the symmetric product of delta copies of the curve. And so this becomes delta plus G. And in here we have again 2G minus 2. And now, for delta smaller than G, generically, H0 will be 1. So we have, so this H1 here will be minus the degree, which is, so plus 1, which is H0 of this bundle. So we're computing that, right? So it's this plus minus the degree plus G minus 1. So, and the degree in this case is delta. So minus delta. So altogether, total, we have 4G minus 2 in both cases, which once we projectivize is precisely half the dimension of the moduli space. Okay, so since my time is up, let me stop here and please ask any questions you may have during the break. Thank you.
Ooh, sorry, I was muted. So thank you, Anna. Let's first thank Anna for a wonderful series of lectures. And we do have time for a few questions. Let's see, do I have someone with their hands up? Don't see anything in the chat box and I don't see any hands. So maybe I'll just ask one thing. So Anna, quickly, could you say, so what is different between W delta for delta less than G and delta greater than G? I think that's what you wrote at the end, but it was not easy to follow.
Yeah, it was a bit quick, right? Yeah, so the difference is, it's if you see what I said, I'm using genericity assumptions. So generically, for a delta greater than G, so by Riemann-Roch, we have that H0 of F1 F0K is greater than so greater than G, sorry. Greater than 1. So we have too many Higgs fields, right? For the wobbly locus to be a divisor. Remember the picture at the beginning. We had the wobbly loci here. And then we have the Higgs fields flowing down. If this is the normal space, if we have too many Higgs fields, then it won't be if generically we have too many Higgs fields, it won't be a divisor. Okay, and in this case, all Higgs bundles have at least 2 Higgs fields, so it won't be a divisor. Now, if delta is smaller than G, then H0 F1 0K equals 1 generically. It's not always the case, but for most bundles, it is. So maybe let me take advantage. Is it clear now, Aswin? Does this answer
I
your
think
question?
that definitely helped. Okay, so the W delta for a delta greater than G, they also occur in some particular component of the nilpotent cone for every value of delta, or am I?
Mm-hmm. No, yeah, they appear. So what happens here is that the nilpotent cone for delta, all the values are valid. So for every delta, one has a component of the nilpotent cone. This is the image of the F tilde that I had here.
Mm-hmm.
Not here, but here. Yeah, I mean, it's not very clearly stated. You're totally right to doubt.
Is the point that for some values of delta, the projection from the nilpotent cone to I don't know if it was the Z or okay, so the projection maybe to the bundles, you lose one dimension, but for some other
That's correct.
you lose more, and those are hence
exactly
divisors. That's the point.
Exactly. So for delta, at most G, this is generically a line bundle, and therefore the same happens here because it's going to be injective generically. But for delta greater than G, then there will be too many Higgs bundles. Yeah, this is what's happening.
I see. Okay. Okay, I think Duong has a question.
Okay.
Duong, go ahead.
Hi, Anna.
Hiya.
Yes, I have maybe a very naive question. So, in the proof of showing that if the hitching map restricted to VE is not proper, then we have a limiting point with an unstable bundle. I thought when we say that we already restrict the hitching map to VE, so now what we're talking about is just the proper or non-properness of a morphism from a vector space to another vector space, right? So why do we?
I'm not sure I understand. So
Why do we?
The point is.
Yes.
Yeah, I think I know what you mean, but the point is that you can prove that properness of the hitching map restricted to this vector space is equivalent to properness of the vector space as a subscheme of the moduli space. And then if it's not proper, then you have limits outside of it. This is what I'm using. Is that your question?
Yes. Okay. So we need that somehow properness of the restriction is equivalent to.
Yeah, and that follows from properness of the hitching map and the evaluative criterion for properness. Yeah. Okay. You want me to write it down?
Oh, that'll be great. Yes.
Okay.
But yeah. Okay. Yes.
So let's see if I get this right. I always need to think about it. Okay, so we have the hitching map. We know that H is proper. Okay. So suppose that we have VE, which is a subscheme of the moduli space, which in turn maps to the HMI. So we have a proper map. So clearly, if and the composition is HE, right? So it's clear that if VE is proper, then HE is proper, right? Because it's the composition of two proper maps, nothing to prove.
Yes.
Do you agree with that?
Yes.
Okay. Now, suppose that it is HE that's proper. Whatever. This is equality. Okay. If HE is proper, then there's a so we want to check that VE is proper. So what we need to do is to, map a curve with VE, with a limit in here. How is it? I always get confused with this criterion. So that's correct. Yeah. So we have a proof. We have a little curve here, a curve with a limit here, right? And the generic point in here. And what we want to see is that, that's these lifts, right? So let me write it in this direction. Is it? Yeah, exactly. Yeah. So we want exactly. Sorry, I need to write it in this direction. Okay. So we want to see that these factors are here. See?
Mm-hmm.
Okay, but since H is proper, so we compose these two. This gives a map here, and this also gives a map here. But H is proper.
Mm-hmm.
No, sorry. Yeah, H is proper. So I'm just confused because I have this here. So let's write things here. Okay. This is P. So this is proper. Okay, sorry, I'm not seeing it now, but this is very easy. It's just the properness criteria, the evaluative criterion for properness, but I'm writing things.
Yes, I think you want to use the universal definition of properness, yes? Or...
Yeah, that's correct, but it's just saying that you can, since H is proper, I want to see this exists. So since H is proper, you can lift it to here. Sorry, so I'm assuming, no, sorry. I'm assuming now that HE is proper. Okay, right, this is HE. Okay, so since HE is proper, then you can lift it here by properness of HE, okay?
Mm-hmm. Yes.
But then you're done because you've already lifted. So it's very simple, sorry. I just messed up with the, okay. Is that clear, Duong, now?
I think I will need to look at it again, but thanks.
Okay, but really it's just the properness criteria, the evaluative criterion for properness. So I was getting confused between which map I assume is proper. Mm-hmm. So if I assume this map's proper, this is just composition of two proper maps. If I assume this map is proper, it's just, properness of the Hitchin map, okay? And properness of this guy.
Okay.
Okay. Thank you, Anna. Again, thank you for the questions, Duong. So let's thank Anna one final time before we close this particular event.